Hi. This is a talk on 12-factor applications. It's a methodology for building software as a service systems. So first of all, who the hell am I? So at the moment, I'm the head of engineering at Just Eat. I don't know if you know, we've kind of just opened an office in Bristol. I live in Bristol, obviously, and I'm from Stoke originally, which is why I've got a weird accent for a Bristolian. So the first thing to do is go through a bit of an introduction about what 12-factor applications are. So it's a methodology, agnostic to language, so it doesn't matter what language you use, to build applications that intend to minimize developer onboarding, so guys who work in teams, and when you start at new companies, you know that's a real pain point for a lot of companies. Exhibit portability via a clean contract with the OS. So that is to minimize the kind of cohesiveness to the operating system or the underlying execution platform. That are deployable on modern cloud platforms, so AWS, Heroku, all those kind of words with cloud in them at the moment. They embrace continuous multi-environment deployment, and they scale without tooling or architectural changes. So if you go from 1,000 users to 100,000 users, the major change point shouldn't be that you are refactoring your code, it should be you're just adding more. So a little bit of a background of this. It's not my idea, in fact I had nothing to do with it. I just think that it's a really interesting architectural methodology to look at. So it's formulated by the guys who founded Heroku. Heroku was the first kind of really well-adopted cloud platform. Originally it was founded on a bunch of guys doing Ruby on Rails applications. It was since been bought for $300 million by Salesforce. So it's a big deal now, and it's really cool, so you should check it out. It's the distillation from them observing and measuring the about 4 million applications that have been run and executed on their platform over the past 7 years. They've obviously witnessed some applications do nothing and others go huge. So one of the big ones was Rap Genius. I don't know if you've heard of it. It's where people put meanings behind rap lyrics on the internet, whatever. And while watching that and interacting with those developers, they've built up this set of best practices. And the idea is to increase developer collaboration and minimize software erosion. So it's also motivated by the idea of removing some of those systemic problems that they've seen people face when being on a cloud platform like Heroku. And they've come up with a set of fairly simple architectural solutions that if you abide by them, you don't hit those problems, and they've come up with a bit of a vocabulary for it as well. So those are the 12 factors. So it's code base, dependencies, config, backing services, build, release, run, processes, port binding, concurrency, disposability, dev and prod parity, logging, and admin processes. So I'm going to go through each one individually and try and explain what they state is a good intention and why they, well, at least why I believe that they claim that that's to be the case. I'm probably going to miss a few of them or kind of short circuit a few because 12 of them is going to take a little bit of time to get through. Okay, so first one, code base. So they claim, or the intent is, that for each individual application that you deploy, there should be a single code base, and it should be tracked in version control. And most people here will just go, yeah, obviously that seems to be the case, but it's a fundamental building block of the process as a whole. Multiple code bases are actually a definition of a distributed system. If you've got 3 code bases all interacting with each other, that's not an application, that's a distributed system. Multiple apps sharing code. As soon as you identify multiple apps sharing the same body of code, then that's a dependency, and that should be extracted out and controlled using dependency management. There will also be the possibility of a single code base being run multiple times. So the diagram here shows that code base running in multiple environments. So in production and staging developer 1, 2, X. So the idea is that that's the same code base across all of those deployments. Now it may be at different versions, but ultimately given the fact that it's a code base and using code control, you have a monotonically increasing result set of that code, you can always go back to any point and identify an individual version, an individual state of that code base. So why? So the first thing is it shows a clear audit history for code, powerful for anyone in teams. It trivializes rollbacks. So one of the biggest issues when you're going live is somebody's done, it's broken. The idea is to roll it back as fast as humanly possible. And we had an example when I used to work at Voucher Cloud when we deployed a load of long cats to the main page. And it was pretty important that we removed the cats from the main page. It establishes a clear, visible progression to live, so you can identify code as it goes through environments. So you can see that somebody has produced some code, they put it into a staging environment, it's been checked, it goes to live, it's the exact same code base. It facilitates concurrent team development, so if you ever worked in a large team, sending bits of code back and forth using email or writing in individual files and things is hell on earth, whereas where version control enables that. And it minimizes inter-app refactoring risk. So that goes back to the point around shared code bases. So the idea that one person makes some refactoring in one code base, it can obviously affect other code bases. So the second point, dependencies. So I kind of touched on this a little bit. So the 12-factor way is to explicitly declare and isolate all dependencies. So that's based on the name, i.e. what it is, and the version of that dependency. To make use of vendoring and bundling of dependencies. So the idea is within your code base, not only do you have the declarations of those dependencies, but when you deploy that code base, you take those dependencies, you wrap them together and you push them out. You utilize tooling to automate the download and upload of updating of dependencies. So obviously we've all got hundreds of dependencies in our code. It's incredibly difficult to identify when dependency A needs an update compared to dependency B. Certainly when you start getting collisions around that can be really, really painful. We used to have a phrase called DLL hell, where you've got multiple dependencies, all of different versions, and it becomes a nightmare. To never rely on implicit existence of system tools. So that is the idea of shelling out to your command line and running image magic, which, back in the PHP dark days, that's what we used to do. And to never rely on the existence of system-wide packages. So that is the idea of a package of software which you have not defined, not declared within your code, but just expecting it to be there. So again, dependencies, why? So the reason that you want to keep these dependencies really explicit in your code base and vendor is that it means that you've got a really clean contract with the execution environment. So if you imagine I've got one code base and one deployable blob, I can push it onto box A, box B, box C, because it doesn't make any assumptions about what's already on those systems. It provides guarantees around inter-deployment consistency. So again, for a similar reason, if you imagine I want to deploy it in staging and live, it's really nice, or in fact, really, really valuable to have that same code base, and not only the same code base, but the same dependency structure already in place and ready for me to just push onto that next thing. It gives me determinism. It outlines explicitly some of those dependencies. So historic projects sometimes had a folder called third party, and another folder called stuff, and another folder called things that Roger downloaded on Wednesday. And we pulled half of those dependencies in here, there, and everywhere. As soon as you decided you wanted to change a dependency, you had no explicit way of identifying what was already in there, or whether there was an issue with any of those things, if there was a security vulnerability. So it makes it really explicit. I've already explained kind of why the updating dependencies, the tooling around the dependencies is useful. Security vulnerabilities in certainly the web world are huge at the moment, and almost kind of every other day you hear about some issue and some vulnerability being identified. The ability to update all your dependencies kind of instantaneously is really valuable. And again, it minimizes new developer setup friction. So if you have a code base that kind of knows how to build itself, because it's got a set of dependencies that are well defined, when a new developer comes on board, They download the code, they hit build, it grabs the dependencies, uploads it, and you're ready to run. So straight away you've got that developer working and producing software. Yes. So sorry, by the way, if this gets really dry. So the next thing is config. So kind of similar to dependencies. In fact, I like to consider config to be almost a dependency in and of itself. But the important things for 12-factor are that you extract those dependencies out of your code. So all your magic strings, all the bits and pieces that connect to third parties or software vendors, you pull that out and you make sure that's in a config system. In 12-factor, that config system is the environment itself. So going back to the diagram from before when we had staging and dev 1 and dev 2, each one of those is an environment. So you can imagine that being an execution environment. Ideally, we want to push that config into that environment, and the most obvious way is through environmental variables. Environmental variables are kind of a dirty word because they don't feel like something that we should be using anymore. But when you can create a new environment and you can set those environmental variables kind of as part of the creation of that environment, they become a very powerful tool. One of the reasons behind that is that they are totally ubiquitous. They are available on Windows, on Linux, on Darwin and Unix versions. They allow a very simple mechanism for passing through information to a piece of running code. The only exception to that is config that doesn't change. So config is really, by definition, the thing that changes between deployments in environments. And so any config which really doesn't change in that instance, then that's kind of fairly valid. I think the general gist is to not do that, but if there are kind of very explicit config details for a piece of software, if you're a Java developer, there might be some large XML document that defines how your parser runs. That isn't really config, it's the configuration of a module as opposed to the configuration changes that make an execution environment happen.
That's a question.
Yeah.
Doesn't this break your principle of encapsulating everything within the code base? This is an expectation of something that exists by magic outside of your dependency tree.
So yes, it absolutely does. The reason behind that is that it itself is well defined in the framework. So there is that one exception that your config comes in from the environment, but it can be expected to be there because the process of building a 12-factor application states that you can expect that to be there. The reasoning behind that is that if you were to embed things like your configuration into your software, things that are very frequently in configuration are passwords, usernames, critical issues like that. As soon as you push that into your code base, deploying it into multiple environments or exposing it publicly is obviously dangerous. And also, even though you want the minimum change between environments, so you want dev to look like production ideally, there will be config changes, whereas there won't be code changes. So that's the kind of decoupling. The way I like to think of it is it's like the variable.
But you need a canonical place that owns all of this information.
Yes. So
why do you have a canonical place that owns this information that's outside of this process, and then you now need two mechanisms for controlling them?
Yes, so you're absolutely correct that you would, in an ideal situation, what you would expect is you have a code base and a config base, and they are separate entities. They should ideally both live in revision control software, so you can do auditing and things, but ultimately one is a configuration of the other. They are not identical. If you embed that other thing into the code base, it means that if you want to make a config change between environments,
so how do you manage maintaining the schema of the config if you're not maintaining it within your main code base?
So there is no real schema other than the fact that there is an implied knowledge between the two systems. So because the config lives in environmental variables within the environment that it exists in, the code base only needs to know the members within that config that it cares about. So for instance, database connection strings or a particular variable that it's interested in, it knows implicitly how to extract that from the environment. No?
I'm just confused that an external dependency of data doesn't have to have a schema. Because anything that consumes data has to know what shape that data's in and what exists and what doesn't exist.
So that something that's not defined in the kind of the mechanism that is 12-factor. That schema, I think, is fairly loose. Adding and removing configuration values. I understand what you're saying. So the idea being that you could deploy some code base that expects config value X to exist and it doesn't exist because the configuration is incorrect. Am I right?
Yeah,
is that where
absolutely.
you're going? So yeah, absolutely. I think you're correct. In there has to be an implied knowledge there.
So we're talking about implied schema.
Yeah.
So,
yeah.
Surely this really busts open the idea that we have of an implicit whole root of dependency management. Then.
So the dependency management is really locked down to the code base. So the idea is that you can identify, given the state of a release, because I'll show you in a little bit, but it gets a bit better. But what you can identify is, given a particular environment and a particular release state, you can reproduce that release state exactly and therefore debug into it. And I suppose the way that this would handle that weak schema situation, in a similar way to something like NoSQL, etc., is to fail fast. So because you're running the same code base on your local computer as a developer, you're going to notice those issues straight away. But you are right, it's an implicit schema, and probably not ideal. So maybe it should be 13 factors. Okay, and then the last point here is consider config to be explicit to the deployment, not as a group. So I don't know about you guys, but I'm certainly guilty of this one. I have a config that I call production and one called test. But actually the best way in the 12 factors to think about things is each individual deployment of your code has its own config. And it's regardless of where the kind of root of that config is, that config is for that particular instance of the system. And so it gets away from this idea that you end up with 1,000 different groups of config. So, there's staging, live, test, and Roger's computer, and John's computer, etc., etc. The idea is that each individual one has the config of this particular deployment. So, why? So config, ideally, is everything that should change between deploys. They can be seen as deployment variables, as I've said. The idea is that given one particular set of code, and you apply a config to it and then run it, that becomes like a unit of state that can be reproduced. If you want to make a modification to that process, ideally you should be able to do that through config alone, so that becomes the only moving part. So it's moved that kind of movement into a single place. Again, config may contain credentials that should be restricted. One of the kind of really easy questions is, can this code base be made open source straight away without compromising us? If you can say yes to that, then you're doing it right. And grouped configs aren't very scalable. So hopefully by the time we get to build, release, and run, it might help with the question you had. So backing services. So this is one of the real big ones, and I think that a lot of development is now moving towards this anyway. So the idea is to treat backing services as attached resources. There is no distinction between your resource or a third-party resource. It could be your database, it could be a database being run by somebody else, it could be your search API, or it could be one that you've found on the internet. You should treat those as identical. There is no magic around the fact that it's your database and you know that it won't go down because on Wednesday you did a backup. The beauty of doing that is that it means that each backing resource can be attached and unattached at will. So if we go to the why, if you have a misbehaving resource for some reason, you can swap that without changing your code. It's just a config change. If your config points to box A, you can change it to box B, C, etc. The environment can expose relevant resources by pushing the config into the environment. It means that when you make a deployment and you want to do a test deployment, that test deployment knows that it's a test deployment. The code doesn't care. The code doesn't know that it's running on a test deployment. It's just configured to point at a thing that just happens to be the test database. And it prevents vendor lock-in for the same reasons. So build, release, run. So the intent here is to have strictly separate integration stages. So build is when you take some code base and you bundle it into an executable bundle called a build. And that includes vendoring the dependencies, pushing in the assets, etc., etc. You end up with some form of blob. The release step is to take that blob and associate it with a config. Now that config is environmentally specific. So if you're doing a release that you want to release to a test environment, for instance, you do the build, that's consistent across every single environment. You then do a release, which takes that build, combines it with the config, and then that config and build becomes what's called a release. That release can then be run. The beauty of a process that creates a single blob at the end, which is a config and the build, is that it is enriched in a way that makes it incredibly quick to reproduce. And that's where we come on to kind of why we want to do that. The run phase is historically one of the most complex, and the idea behind 12-factor is to switch that on its head and make it the easiest. I suspect most people have been in a state where they've been installing databases on boxes to try and get an environment to run. The beauty with this is that the idea is that once you're at that run stage, you can kind of throw it at any reasonable environment and it'll just work. So it restricts runtime code and config mutability once it's built into a release. So once you've got a release, you push that onto a box, you push it onto 100 boxes, you know deterministically that that's running version 1, 2, 3, 4, 5. And if you want to run 1, 2, 3, 4, 5 again, you just create that release again, or you grab that release and it should run, no matter where you put it in the world, should run the same. It facilitates continuous integration because it's got these very simple steps. You know, as somebody who sets up a continuous integration process, what you need to do and how you need to get that blob out at the end. It's auditable, so very similar point to the first. It allows automated re-execution and scaling of releases irrelevant of hardware state. So if you have a runtime blob that's ready to run, it's configured, it's got the code base there, if the hardware goes down, the answer to get it back up again is create some new hardware and throw it at it. If you want to scale, you throw it at 10. The idea being that if it will run in one place, it should run everywhere. And yes, as I say, it minimizes run complexity. The next is processes. I'm going to be fairly swift on this one, but the idea here is to every single instance of the application should be stateless. It should share nothing. And any kind of state that sits inside it should be residing in some kind of stateful backing service. The idea is that there should be never any assumptions about the execution environment other than the configuration. The idea of caching something on request 1 and then expecting it to be there on request 2 means that you're anticipating that your software is going to be continuing to run on that box. It may well be that the next time it executes, it's been failed. The hardware might have failed, the process might have failed, it may have been brought back up again. So you can't make those assumptions. It should be also servable from any individual instance. So if you imagine you've got 10 of these, each request that comes in, any one of those 10 should be able to pick that request up and act on it. And then any use of the transient file system should be really discouraged. So the reason this is only really discouraged and not kind of a flat-out rule is the fact that sometimes certain images and things, when you execute your blob for the first time, you may want to build. You might want to bundle your CSS, for instance, or you may want to bundle your JavaScript and put it in a hostable place on the file system. As long as that's repeatable, it's not so bad. Ideally, you'd push that all the way back to your build step, and so that's already in there. Anything that's kind of being generated at runtime is questionable from a kind of 12-factor point of view, other than the output, obviously. And the reason behind this, kind of touched on them as I was talking, the robustness across restarts, redeployments, and configuration changes. If I go into a system and it's running, we've got live traffic hitting the systems, and I want to make a configuration change. I want that to propagate across all my instances. I make that configuration change, and I restart that instance. That straight away starts serving the new valid configuration. The beauty of that is that from a user point of view, you've not even witnessed that, because the whole system's built around the idea that if I fail, I just start again. It's agnostic to the underlying hardware and memory state, obviously a massive win if you don't touch it. And it gives a massively simplified request routing process. If you know that all you have to do is send it to any one of the available boxes, then that's a massive win compared to things like sticky sessions, where we have to remember through cookies, and then it goes to the wrong one, and then that fails, and then you've got a user who's getting in a really bad state. Port binding. This, for some developers, I think is really, really strange. And I think one of the most contentious parts of the document. The idea is, because you're not expecting or anticipating any system-wide processes or software to be installed on the machine that you're expecting, you can't expect the injection of a web server. So for a Java developer, that would be Tomcat, for instance. For a .NET dev, it might be IIS. You can't expect those things to be there because they may not be there. Certainly, they may be different between versions, and so that becomes very difficult to determine again. So the intent is to have a single port which you connect to and you bind to, and then you serve requests on it. So it's protocol agnostic. These things don't care if it's HTTP or HTTPS you're caring about, or XMPP or any of the other processes or protocols that we use. The idea is that you just choose a port, or actually the environment chooses a port for you and tells you which port to bind to, at which point you connect and you start receiving and serving requests. This also allows any other app to become a backing app of another app. So as long as the environment knows how to wire those two things together, which, because it's executing both potentially, it means that it can auto-discover those kinds of things. I've gone through all those. It also simplifies multi-process and multi-tenanted environments. So if you imagine we've got 10 or 15 instances of an application running on a single piece of hardware, if the environment can give each one a different port to bind to, it's effectively automatically using the internals of the system to route all that data around. Concurrency. So this is probably the core win, or historically was considered the core win behind this whole system. So we're all pretty aware of these kind of things now, but the idea is that you can have total scale out because you've got processes which are stateless, you've got systems that are stateless, and all state is in backing servers which are shared amongst all instances of that system, and therefore you can scale out just by adding more processes. This means that you can have an arbitrary scale of a platform. Now obviously there are question marks around how much your backing services can handle, but if you make the light assumption that those backing services can cope, then the application itself can scale arbitrarily. Each individual process shouldn't be able to span more than one machine. So some systems historically have been laid out in such a way that even though they're dealing with a single request, they're spanning across multiple machines. Again, that goes back to the first very early point about that being a distributed system, not an individual app. And they should rely on the execution environment to handle things like process restarts, crashes, and shutdowns. So a lot of software, certainly in things like the Erlang world, you have guards and you have protection built into the infrastructure to restart processes. Well, a lot of systems already have that built in at the kernel level, at the OS level. If you start a process and it fails and it dies for some reason, it's not necessarily in this system the job of the software architect to care about that. It should just assume that the underlying execution platform will handle that for it, and that might well be by restarting the process inside that particular piece of hardware, or it may well be starting an entirely new piece of hardware entirely, which obviously simplifies code base. why is this concurrency really powerful? So obviously it allows the simplification of your application. So handling things like multi-threaded environments, multiplexing of requests, things that certainly in the Java world were a fairly major issue back in the day, and exploiting all of the parts of a piece of hardware. So maybe you've got 50 cores on your processor. One way of doing that is to build a complex application which multiplexes those requests down and handles that. The alternative in the 12 factor is to let the OS do that. So instead of having one instance of the application, you have 12, each one given a call. It doesn't, on the other hand, preclude you doing that. So if you do have software that requires that or is advantageous to do that, then there's no real particular issue with doing that. It's just no longer needed. As I say, adding additional concurrency is trivial, so scaling your system up for more requests or handling more jobs is trivial, just add more systems. Disposability. How am I doing for time?
5 to 10 minutes.
5 minutes. Okay, I'll be really quick. Disposability. So this comes to the idea, again, going back to the idea that at any moment, any process can be killed off, can be restarted. Applications should be able to handle that. Typically, a lot of applications don't handle that kind of thing. They need to kind of stop gracefully. Those are a set of assumptions that you can't make. The intention is that you may be on 1 second, off the next. You may have you'll be able to handle one request and not the next. So part of the idea behind restarting or creating new instances very, very quickly is that startup and shutdown should be very, very fast. So grabbing a load of data from the database and building a big in-cache model is not an applicable way of doing this. The environment may well send a SIG term, so that's a system call that should tell that system to turn off as gracefully as it can. Now, if you build everything really, really well, then you shouldn't really care about that. It shouldn't matter, because you should always be graceful, even if you're instantaneously turned off. But given an ideal situation, the environment will warn you that it's about to kill you. Workers, if you have a worker process as opposed to something that's just handling requests, so something that's consuming off a message queue, the behavior of that, if it receives a request for a graceful shutdown, should be to stop working straight away, put that piece of work back on the queue, and turn off. The idea behind that is that it means that you can scale up and down very quickly. It's not the easiest thing to achieve. It basically means that you've got to be idempotent and kind of build around a crash-only architecture.
Sorry, what's crash-only architecture?
So it means that it's reentrant. So the intention is that a crash-only architecture expects to have been crashed at any moment. So it expects when it starts up that it has to go through the recovery phase. It can't expect that, oh, I've got a lock file that says that I gracefully shut down last time. So the intention is that no matter what, you should always start as if you're expecting to start recovery from previous fail. And it may be another instance that's a failure as well. So again, this enables the elastic scalability, because you can add and remove instances nearly instantly. As soon as you want to shrink your property, you just turn a load of boxes off and they handle that. It aids robustness, and it does that through process migration. So for instance, if you have an environment that's smart enough to identify that a particular bit of hardware is using too much of its CPU or some particular process, it can switch that one off and turn another one on instantly. So you can load shift your entire platform across a set of machines. And as I say, crash only and therefore reentrant is the only way to do those queues. So there is a set of requirements on the application that in order to fulfill these roles. The last three are much less important, but they help as a developer. So dev and production parity. The general gist of these two slides is that you should try and keep each one of your environments as close to the other as possible. So if you're a Redis developer, historically you would create your local version and hit SQLite, and then when you went to production you go to Postgre. The issue is that is actually a fairly leaky abstraction, and it's certainly not behaviorally true. So, for instance, things like the way that Postgre deals with indexes versus the way that SQLite deals with indexes, it means that you're actually not testing the real thing. Now, it sounds like a tiny thing, but if you multiply that across all your backing stores, you may end up with a system which simply doesn't handle or behave in the way that you've expected. So the general gist is to try and have your local environment or all the other environments as close to each other as possible. That also means try not to kind of hide those dependencies behind abstractions within your code, so ORMs are the most obvious ones. Logging. So again, a bit controversial, but the idea behind in 12-factor is to log everything, log as much as you can, and log it to standard out. The intention being that the environment will capture standard out and handle the rest of it for you. So we've all set up configs that send your logs to X, Y, Z, and it has to know how to push it to S3 or not. That level of configuration in there is unnecessary if the environment can handle it. So it's dumb app, smart environment. So as long as your app pushes all its logs out to standard out, the environment will capture that, and then it can be configured to root anywhere. So your entire environment, there might be 100 computers, 100 machines in there. They all know that the general behavior you want to do is push that data into S3 and also maybe push it into something else. So for instance, it could go through an analysis system like Splunk or Kibana, those kind of things. It also means that if you are rerouting your data, so for instance your S3 buckets have run out and you now want to push it into, I don't know, somewhere else, a hard drive, you don't actually make any code changes for that. Again, it's outside the code base, so it just means that the environment needs modifying to deal with that. And it also means logging is substantially simplified. And then the last one is admin processes, and I think this is probably the most controversial of all, but I think it's an interesting one. So the idea behind this is that when we run admin tasks as developers, we tend to just log into a machine and make a change, do something, run a script, etc. And I don't know about you guys, but I've watched a lot of people make huge mistakes. I've watched people take databases down just by making an incorrect judgment about the environment they were applying something to. They thought they were killing the test database, but they actually killed live. So the idea behind using admin processes as single one-off processes is that your admin processes should be built into the code base that you're deploying. They should be reactive and responsive to the same config as they're deployed, and they should be executed from within the environment which they are currently executing. So the idea is that you would send your config, your admin instructions into your code base. When you deploy to production, that's when you would run your migration, for instance, on a database or some other admin task. And the intent behind that is that it almost can't go wrong because it doesn't have access to any of the environments that it shouldn't have, because its configuration is correct for production. Obviously, if it does go wrong, then you've got something else in your code base wrong. And then there's a slight preference for languages that use REPLs. And the only reason for that is that if you want to run these kind of admin tasks, it's much nicer to be able to log into a language like Erlang and run those admin tasks from a REPL as opposed to wiring up a weird HTTP endpoint that you can type a magic string in and it runs that execution. So yeah. So I've gone through all that. So that's 12-factor applications. I'd say any questions, but I don't think I've got any time. I haven't. There's a load more about 12-factor applications at 12factor.net. You can see me at LinkedIn if you want to get in touch, and feel free to do so. And if you're interested in a job working at Just Eat, where we work on this and an awful lot more cool stuff, feel free to go to that URL. And there's a load of jobs that we're currently looking for in Bristol to run the office. Cheers.